Myriad of Conferences. Now I have the pleasure of presenting you Dr. Gustavo Martinez-Meckler. He is from the Institute of Physical Sciences at U.N.A.M. and works with nonlinear phenomena and complexity.
Can you hear me well? Is this okay? Fine. Well, I guess the first thing I want to say is that I'm very happy. It's not often that one finds such a mixture of people working on so many different specialities that get together to try to solve. No? Oh, I was saying I was happy. Did you get that? I'm still happy. No, what I was saying is that it's a unique opportunity to be with such a mixture of people that work on so many aspects of a problem, and the problem is really trying to understand biology, to understand life. I'm personally a physicist at heart. I enjoy mathematics, and I'm fascinated by biology. And suddenly I find here so many people that share that feeling. Very in particular, Jose Mendez, who's the person I want to present. I would dare to say that I think that Jose is a physicist, and I wrote here, seduced by the enchantment of complex systems research, in particular in the context of networks. And he has worked on many areas, amongst them biology. Something that has been mentioned here several occasions is the word complex systems. And since he works on the evolution of complex networks, amongst other things, I would just like to mention a few words about complex systems. As has been mentioned already, that they consist of systems with many interacting components. There's nonlinear interactions occurring there. There are feedback loops, positive, negative. They display collective emergent phenomena. It is sometimes said that the whole is bigger than the sum of its parts, this idea that you see the whole system and things appear there that you wouldn't suspect before. For example, maybe in languages, the emergence of meaning, or other examples have been given here. There is a hierarchy of levels of description and organization. Also, there's another aspect that I guess would be worthwhile mentioning, is that these systems, since they have many elements and they have this type of interaction, when they evolve with the dynamics. This sometimes takes a long, long time to get to its steady state or to its equilibrium. And in that sense, they are systems that live very much in transient periods. And that's something very interesting, because then often you can have a system that the transient's so big that changes in the environment take place before the system itself gets to its equilibrium or steady state, and then it has to adapt and kind of reconfigure its goals. It was mentioned by Evelyn Fox that complex systems look for disorder. I don't quite agree. I think that you have the complex systems, but you have a dynamics on it. And sometimes that dynamics does go to attractors, it is regular, and it self-organizes. So there's also an element of ordering inside these systems. Of course, the field was born from statistical physics, many aspects of it. Others come from systems theories in engineering, for example. The work that you do there is transdisciplinary, interdisciplinary, multidisciplinary, and it often establishes bridges between different areas of knowledge. And something interesting that appears that you get these universal I would just like to take advantage of my presence here to mention that in Mexico, complex system studies has been taking place since a long time ago. Since the 1990s, there was a Department of Complex Systems, which according to the director of the Santa Fe Institute, it was the first such a department, was the first one worldwide in terms of being recognized by university as a department. And also there's a Center of Complex Systems that's just going around the road, which is kind of about to be inaugurated by the end of the year. I guess to give an example of the feel I have of the subject, I would like to give a very brief summary of a problem that we have been working on. It has to do with fertilization, essentially how a sperm swims and gets to the egg. The egg has a coating, and then this diffuses, and then there's chemotaxis. It tries to get to the egg. The point I want to say here is that in the case of sea urchins, which we study, and there's going to be a talk about that too, but at another level, they swim in circles, and they look at this gradient of the chemoattractant. So there's a cyclic behavior of their swimming, and that gets coupled with a biochemical signaling pathway inside the flagellum. And so essentially what I want to say is that there are two oscillators that are coupled there. And there's a lot of physics, a lot of chemistry, a lot of biology inside there. The point is that this signaling pathway can be viewed as a network, and that's what brings me to the subject of Jose. And what we have done is by studying this network, we have been able to kind of address issues which cannot be addressed if you make single experiments. They are issues that have to do with the whole of the system. And you can do some predictions that experimentally would be extremely hard to realize. As a result of that, we have been able to do predictions. We have understood the behavior of multiple drugs that have multiple sites of attack. We have also understood things about the electrophysiology, etc. No? But the point I wanted to point to stress is that by studying this, when you look at the dynamics, something we have found out is that the dynamics lives in a critical regime, which I expect you will be addressing criticality. And this critical behavior is in between order and chaos. And it's a system where it has all sorts of kind of correlations at all distances. And this is one more instance of many other cases, neural networks, genetic networks, metabolic networks, etc., where this criticality appears. And the idea of this criticality is that most probably it's one of the cases in which you have the best that information is transmitted optimally. Again, this is not an idea of something being very random, but there's this fact that you would like to have the best transmission of information, and that could have some consequences in evolution. When you look at the complex systems, you can look at genetic regulatory, the ones I had mentioned before, ecological networks, historical contingency, finance, economy, electric grids. But the point that maybe is very interesting is that there's a very big element of surprise when you study these systems. So all of these things have been looked into by Jose Mendez. He is an author of a book. It's called The Evolution of Networks from Biological Nets to Internet and the World Wide Web, which is it's like a turning point. I mean, this book has been it's a reference that everybody that works on this subject has looked into it. The book is from 2003, I believe, and it still is a book that solves problems that are presently of interest. He also has a review of critical phenomena in complex networks, which is also very much consulted. He has worked in the growth and evolution of complex networks, percolation in particular, criticality in networks, self-organized criticality, neural networks, language, tourism, sports, internets, social organization, rumor spreading, amongst others. José is a professor of physics at the University of Aveiro in Portugal. He was head of the department, the physics department. He's director of a research unit there and also president of the laboratory, the 3N laboratory. It's an Institute of Nanostructures, Nanomodeling, and Nanofabrication. And since February 2010, he is vice director for research and doctoral studies in the University of Aveiro. In 2004, he was awarded the Gulbenkian Ciencia Award. And the Gulbenkian Institute is a remarkable institute worldwide known in which all this type of interdisciplinary work is done, and it has some incredible educational programs. He has been invited and has had research periods in the University of Porto, Oxford, Geneva, CUNY, Sao Paulo, Nancy, and Minas Gerais. So it's a privilege to be able to give you, to ask you to give your talk. Thank you.
So, thank you very much for the introduction. It was very nice. First of all, I would like to thank the organizers for inviting me and giving me the opportunity to be in this nice country, this nice city. I already have the chance to walk around a bit, so I enjoyed, in fact. So the conference is very nice, lots of people. Maybe it's the conference I was speaker with more people, especially more students. It's not easy to organize such kind of conference, for sure. I myself, when I was young, I organized conferences, and I know how tough it is to organize. The only difference when I organized the conference was I put a constraint. And the constraint is, in that time, that the speakers, I don't think in that way now, but in that time, the speaker should be younger than 35 years old. And when I did that, I can tell you that nowadays, some of the speakers that I invited for this conference, nowadays are leaders, like Barabas and many other leaders in their areas. So I was quite nice in choosing the speaker when they were young, and they became famous. In fact, in one of these conferences, it was in Porto. In that time, I was a professor in Porto. And if you read the book of Barabasi, he just mentioned about this conference in Porto, because it was in '98, and it was when this field of network started. And he claims in the book that instead of paying attention to the talks, he is looking for some facts that the student Rec Albert sent to him, and he's trying to understand why the plot is a power law and not a random graph or something like that. So he says that in the book. Okay, so as it was said in the introduction, in fact, I published a book in 2003 after some review article that we published in the very beginning. So, in fact, it was the first book in this area, so it's in the second edition now. And we are preparing another one because already 12 years passed. And I hope that the only thing, not the only thing in common with this conference is the title, Evolution. I hope something else is in common with your interests. So, as you know, everywhere you can find networks. Nowadays, all people try to model the systems they are studying with networks. I'm talking about social networks, information networks, technological networks, biological networks. So there are many examples out there about networks, and so people get lots of interest on this. Of course, when we talk about networks, we have to understand what are the nodes and what are the links between these nodes. So you have to identify this in this microscopic way, and when you have defined this, you arrive to something similar to that, and then you can study the properties of this entity. This is the things we used to do. Of course, in the area of biology, as you know much more than me, there are many examples, protein-protein networks, metabolic networks, so many people talk about that today, transcription networks, and also neuronal networks. I will talk a bit about the last one because I get some interest recently on this topic, so I will show you some results about neuronal networks. Okay. But so returning to the biological network, so I don't have to explain it to you because you know this, as I said. But say you can identify here two examples: metabolic pathways, protein interactions, or when you go to food webs, you can have also identify what are the nodes, what are the kind of links, or in neural networks. But you know, when we are trying to explain these systems, we have to do, we cannot study the system fully. And so when we look to this animal, so even for biologists, you cannot describe it completely, as we already saw it today. And we as physicists, we try to simplify things, okay? So for us a cow is like a sphere, okay? And eventually he has some tail, but even the tail we put it to tend to zero. So we try to avoid the tail, etc., etc. But the good thing is, once you understand this simple system, maybe there are characteristics on this system that also exist in the complex case. So in the case of the cow. And so if you understand the simple system, then step by step you start to introduce new features and you try to understand. But you have to understand the system by itself, by the smallest ingress, as smallest ingress included as possible. So the question is, how can we model biological networks, so any kind of networks like I show you in the beginning? So, of course, we have to map our system to one of these entities. There are more different networks, but these are the most common. Let's say we have edges and we have links, but links are undirected, so it means that you can go in both directions, like in the internet. So you have a cable in the internet, so it means that signal can flow in both directions. But there are also situations where you have directed networks. For instance, the web. I can point to your web page, but you will not necessarily point to my web page. So I mean, there are directions in these connections. And can also have direct or not directed, but weighted networks, like I show you here. So it means that the different connections can have different weights. And then you can also associate a strength to the nodes according to the weights that arrive to this network. But I will not enter in these details, just to tell you that there are many possibilities of designing these networks. There was a paper in Nature in '98, you certainly all you know this paper about small walls. It's a simple paper, but it was a kind of revolution in that time. Why? Because we usually study systems like those, so regular lattices, okay? It can be triangular lattice, hexagonal, or whatever, but in this case, for simplicity, it's a square lattice, and bidimensional square lattice. And so you can ask how much steps I have to do to go from here to this point. So you see, you have to choose the smallest path or so. But in this case of systems, this average distance, say, depending on the dimension, go in different ways, but you can immediately say it goes in square in the bidimensional system. It goes like square root of the system size. It's the typical average, typical distance in such a system. But what this paper shows was that for some systems, for instance, like this one, where you can put randomly some connections between nodes, in some you have a parameter that is a probability that you connect two nodes chosen randomly, and according to this parameter,
you can have different kinds of behavior, but there is a region, a special region, where you find this called small world effect. Basically, you have short distance. When you are in this regime, you have short distance between the nodes. And also there is they introduced another concept, that is concept of clustering. I will not talk about this here, but it's another characteristic you can measure, and it is a kind of local characteristic, and this is a kind of global characteristic of the network. But so you see, contrarily to this distance, for instance, suppose if you have a big system, square root of a big number, still a big number. But here is logarithm, so logarithm is much, you see, it's much smaller than, for instance, this cubic root of system size. And you can see, for instance, examples here. Facebook is a huge social network, a huge of nodes. However, the average distance between any two guys in this network, see, is 4 steps. How can you imagine, if you don't know that in 4 steps you can connect any two guys in such a network? Or in internet, 3.3 and so on. So depending on network, you have different average distance, but they are short, very small, compared with systems like that. Okay? And this was kind of a revolution in that time. And it was, I would say, the paper that puts me working on this field. It was because of this paper, so when I saw this paper, I came to my colleagues, I said, it seems to me that there is something to do here. And in fact, we proved the first exact result about this system, okay, in that time. But later start to appear many studies, and I show you some pictures about the degree distribution in a logarithm scale for many different systems, as you can see. World web, proteins, metabolic, etc., etc. And everybody is looking for power laws. It's fashion to look for power law. Everybody looks for power law, everybody tries to fit a curve in these plots, okay? Like here, people try to fit, etc., etc. So I will talk a bit later about this again, but just to mention that many studies appear, everybody starts to study all these systems. And people find, like I show you here, so this is a logarithm. This is a logarithm, so people found this kind, it's very tricky, this kind of, instead of this that people expect, so some kind of random graph, so things happen randomly, connections appear randomly, but apparently not. There is some other law behind of it, and people find these kind of laws, and everybody try to fit with this kind of law. So going back to this curve, I have to tell you that the system size and the gamma exponent is the thing you see here, this exponent here. This gamma exponent determines somehow the quality of the result. I will explain. We proved that the cutoff, so the maximum degree you can have in the network, so the biggest hub you can have in the network, follows like that. Forget about this, don't worry about this. So the cutoff is this guy here, is the maximum degree you can have in the network, goes like T is time or network size as you want. If you put a node by unity of time, at time T you have T nodes. So is the size or the time as you want. And it goes like 1 divided this power, gamma minus 1. And this because of this I said the sentence before. So let me tell you the following. We made this plot, I took this from the book, and in physics, when you see a plot, any physicist, when I see a plot log, any physicist say, if it doesn't shows at least 2 decades, the results are not good. You should have 2 decades. 2 decades means between 10 and 100 and 100 and 1000. So you have to have data in a straight line at least between 10 and 1,000. 2 decades, at least. Okay? And so here I assume 3 decades. And making some calculation with this previous formula, with this formula I show you here, you can immediately say where are the good results and where are not. And you see, this is the region, I say here red, but it's not red, here is blue. This is the region where the data is more or less. Why? Because the system size, this is logarithm of system size, so sizes are too small to take good conclusions. Some of these results here are biological networks. Those here maybe are internet, web, because in general biological networks are very small. 1,000 nodes, 1,000 proteins or whatever, but in general they are small. And if they are small, maybe we have problems. So I explain here how to conclude this just based on this formula. And this formula only takes in consideration the system size and the gamma exponent. So going back, so this is not important. Now, so this to explaining why, what. It's almost impossible to get exponents bigger than 3. Almost impossible, unless you have a very big network. This formula immediately shows that. If you remember the formula, immediately shows that. I can go back if you want a bit and look. If you put here gamma equal to 4, let's assume we have a network with gamma equal to 4. If you put here gamma equal to 4, 4 minus 1 is 3, so you have square root of the system size. Square root of system size supposes 10 power 6. 10 power 6 the size of network. Square root gives 10 power 2, 100. So it means that the biggest hub has size at most 100. So you see, you are in the limit, even if all points are straight, you are in the limit of 2 decades. And you have a network with 10 power 6 nodes. It's not easy to find in biology. You see? So gamma equal to 4, it's almost impossible to find. Okay. But some people claim that there are gamma equal to 3.5, etc., with a very small network. For me, it's wrong. Is this dot here, I can tell you, is a paper on Nature about sexual network. So, what kind of networks can we have? We can have equilibrium networks. What I mean by equilibrium networks means networks that have fixed system size, fixed number of, say, system size means number of nodes, fixed number of edges, so means the average degree is constant. The degree distribution gives all information about the system. For these kind of systems, everything can be known by the degree distribution. But there are also non-equilibrium ones, more interesting case. In this case, both things can grow, like the internet. Every day there are new computers connected to the internet, etc., etc. Or in the web, every day there are new documents and new links. Okay? But in this case, 2 situations can happen. Or the system, the number of nodes that I call time, as you see, the number of nodes, let's say 1 node per unity of time, and the number of links also go proportionally. Say every time you have a new node, there is a new link to the old part. So let's assume, if it is not 1 link, say 2 links, but it's still the same order of magnitude. So it means that this quantity is again constant, like here. Okay? Is again constant. But we can have situations that I call accelerated growth, where the number of links compared with the number of nodes, if we apply this formula like here, we can see that this quantity grows with time. And if this quantity grows with time, so if the average degree grows with time, then the situation is more complicated. It's much more complicated to make the analysis of the system. But it's possible to do. Okay, this is also something that I can show you, that you cannot have, if you show me a result with gamma smaller than 1, I immediately put in the trash, because it's impossible. Look, it should be bigger than 1, because it's a probability. If it is a probability, you have, these quantities should sum up to equal to 1, so immediately you conclude that gamma should be bigger than 1, okay? And also, because this quantity is finite, gamma should be bigger than 2. So bigger than 1, bigger than 2, everything should be bigger than 2. Like I showed you before. If you see my previous, look here, all networks have gamma, internet, web, metabolic actors, collaboration, internet, synonymous, citation, sex, the one I mentioned, etc. All of them have gamma bigger than 2. That's okay. That's okay. It's mathematically correct. But it's possible to have gamma between 1 and 2. But it's a special situation. It's this situation I told you that is in accelerated way. I think internet falls in this way, in this regime. But maybe later. I mean, internet is evolving, and in my opinion, the gamma exponent will decrease with time, and will pass from the value 2.1 that has maybe 10 years ago, and maybe today, if people measure again, maybe it's 2 or 1.9. Is my prediction. Okay, about this, so people try to understand why we have these power laws. And then came the proposal of Barabasi. In fact, this concept of preferential linking is more old than this. It was found before in other situations, but okay. Let's assume that it was the first. So you see, you start with something, like 2 nodes and a connection. Then you add a new node, and you can put 1 connection or 2 connections to the previous one. And you repeat this process. You continue to add nodes and edges, but you introduce a new concept. That is the following. Every time you add a new guy here, you attach to previous ones with a probability that depends on the degree of the already existent nodes. And the probability is higher if the node has higher degree. So the probability is proportional to the degree of this node. So higher the degree, higher the probability to connect. Like rich get richer, this concept of rich get richer. So guys that have lots of money, it's more easy to make money. So this is basically the idea. In proteins, it's possible also to, in biology networks, it's possible to guess this kind of process, but I will not spend time with it. So it is a bit complex. Again, Barabasi proposed a solution to this problem, and he proposed in a very special case and with a very simple methodology. We proved in that paper here in 2000 in an exact way the result of Barabasi, but even more complex, in a more complex way, more general way. You can predict all values of gamma bigger than 2. So between 2 and infinity, you can get all values you want. Later, it was proven by mathematicians the same thing. It is also people ask, is it possible to measure, in fact, if there is this preferential attachment concept? And they did some experiment with the internet, so they measured the internet. They look to nodes with a specific degree, and every 6 months they see how this degree changes. And you see, the data is very clear. So you get the accumulated change of this degree goes like k power 2, but because it's accumulated means that if it's not accumulated, it goes like proportional to k. So it seems good results in my opinion. And again, you see, 1 decade, 2 decades, 3 decades. It's quite nice result. And you see, in 2002, Barabasi have a review article, and many models in that time. Immediately in 2002, already many models appear, with some with exact solution, others without exact solution, but many things appear. So lots of people became attracted by this field, very popular field in that time. Let me show you one nice result. I saw this paper by Cacho and Solé in Archive, and this paper is about the word network, so language evolution, as you want to call it. So it's one of the best examples I know in literature, this one here. Because look, there are this size of, the network is very big, and the number of links also very big. And you see, it's clear. So how they construct this network first? So you take sentences from different texts, British National Corpus, and you see in the sentence, for instance, today is a nice day. So today is connected with is with nice, etc., etc. So if the words are in a sequence, you consider they are connected, unless there is a comma or a dot. In this case, the two consecutive words are not connected. That's it. This is the way to construct the network. And they plot it, and you see the result is quite nice. But they found that there are two slopes. Two slopes. This slope here is close to 3. So close to 3, barra base, exponent 3, maybe preferential attachment. Maybe. But this is 1/2 of it. It's 1/2 of it. So they couldn't explain why this happened in this way. And I saw this result, and I tried to guess what is the mechanism, the microscopic mechanism that can produce this result. And the idea was the following. So, preferential attachment, of course. So when a new word appears, it connects, or say, it will be close to other words that already are connect, like is, articles. So articles appear a lot. So for sure it will appear close to an article or something like that. So preferential attachment. But this is not enough, because this only predicts this exponent 3 or 2.7 or something like that. So what else should we include? So we include another mechanism that is the following. Let's assume that, because look, when you have a network, suppose you have 1,000 nodes, another node appears. This node will connect to one of these 1,000 already exists, and so on and so on. But there is no dynamics on the old part. The old part is frozen. Simply, one new node connect to the previous part, another node connect to this part again, and so on and so on. But you don't touch the old part. But we gave the possibility to new words, to old words that appeared before, that never appear together. In some case, they can be together. In some situation, they can be. So some construction that you allow words that never appear together, they have this possibility. And so we did this with a certain probability that is a constant c times the size of the network. I will explain. So this is preferential attachment. And now you see, this is all the nodes, so in principle there is no dynamics between these guys, but we allow the possibility to these guys to be connected with certain probability. And we put these two effects together. When we put these two effects together, we came to a model like that. Forget about this. You see, we know the average number of connections each word has. It's given, it can be calculated by the numerics. And so, putting this together, we can calculate C. So the only parameter that we have in the system is calculated by the data, from the data. And then, you see, our curve is here. This is our fit by this model. And it fits very well, the data. Okay? And we can predict this point here that we call K cross, and also the cutoff. So everything can be predicted by this model. And what is it? What is this area here? What is this area here? This area here is, in fact, the minimum number of words you have to know to speak Spanish or to speak English, etc., etc. Something about the area this area here is about 5,000. So if you know 5,000, you speak well a language. Okay, is what it says from there. I once gave a talk to people from literature, this area, and they told me, because I don't know nothing about that, that this can explain one of the theories of the evolution of the language. By objects or by this, they understood that this can explain. Okay, so you see, the exponent that you get there is 3/2, 1.5 they get, and here they put 2.7, and I get -3 as it should be by preferential attachment. Okay, this is a simple example of a model that can describe the data, but data with quality. Another important thing about networks is the resilience. How robust are these networks against attacks? By attacks, I mean deletion of nodes or links or whatever. Failures in the network. Very important problem. You can see more or less. So the color change here in the screen. You see, I put together, not me, but I took from this paper, but I find it amazing. So they put together plots of two things. One made by God, one made by man. So different ways of construct. But if you look to these curves, they look the same. One corresponds to random failures. So randomly some nodes disappear. Another one corresponds to intentional attacks. So for instance, you want to attack the network, you go to the hubs and you remove hubs. When you remove hubs, you see the size of the biggest cluster, so the giant component of the network where everything can connect to each other, disappear. So you see, in the case of an intentional attack, with a fraction of 10% or even less of deletions, everything disappears. Everything becomes disconnected. If you do it in a random way, you need to delete 80% of the nodes to say connection disappear, or at least big part. Okay? But you see, two different systems and similar curves. So it means the mechanism is the same, for sure. The mechanism behind is the same. And also in this plot you can see that for random attack, the diameter doesn't change, it's constant. So you can find you stop a path, you find another path, and you can get there in the same way. But when it's the target attack, you see the distance immediately starts to increase. So you need more steps to go from, in average, from one place to the other place. Okay. I will pass this part because it's a bit technical, but it's a way to describe a transition. We call it percolation transition or whatever. But basically what you have, you start by having nodes, isolated nodes, and then randomly you put connections between them, okay, with some probability. And so connections start to appear, you see, start to have small clusters, connected, another cluster, another big cluster, etc., etc. And when you increase the average degree, so you put more connections, more connections, more connections, suddenly a huge cluster appeared. So this is the size of a huge cluster. So a cluster with a big fraction of the network, you see? There is only one, is this big one here, you see? So we are somewhere here, I don't know, it corresponds to somewhere here. So almost 50% of the nodes, let's say, belong to the giant cluster. So we are somewhere here, you see, in this plot. So there is a phase transition. We can describe very well this phase transition. Because of this, I will show you something happened recently. Recently, people decide to do the following. It's a paper on Science, 2009. In this paper, they proposed the following. Instead of doing like here, choose two nodes and with priority P connect them. And choose another two nodes and with priority P connect them. They did in different way. They did the following. Instead of choosing two nodes and connect them with priority P, they do the following. Choose two pairs of nodes and connect those pairs that have the smallest sum, for instance. Because, let's go here. For instance, suppose you choose this guy, so this guy belongs to this cluster, and choose this guy belongs to this cluster. So we connect them if the other two pairs we choose has a bigger size together. You see, this is the rule. A kind of model of fitness in this, okay? And so you can have, or you choose the smallest sum or the biggest sum. So if you want to enhance this transition. And what they found, contrarily, this curve here, the black curve, is the curve that I showed you before for the random graph, okay? Is exactly the curve I showed you before. And what they found, you see, this corresponds to this. So you choose this node, you connect them, and then you have a big cluster, etc. This is the process of construction. In this model, you choose this cluster, for instance, this guy and this guy. They belong to this cluster, this belongs to this cluster. And you choose this guy and this guy. Then you look to the sum or this sum, and you connect only one of them. Okay? This is the rule. Simple rule. In computer, it's trivial to do. Trivial to do. And they came to this result. You see? It seems a discontinuous phase transition. So for you, in physics, for people that is here from physics, they know that there are second-order phase transitions, continuous like this, and there are discontinuous phase transitions. There is a jump. So something jump and then goes, okay? Suddenly jump. When you change a little bit the parameter, the system gives a jump. So they claim, that's why they call it explosive percolation, because percolation is this, they call it explosive percolation. Honestly speaking, I listened about this paper when I was in a conference in Italy. And I told to my colleague, for me something is wrong in this paper. For me, and I came again home and I started to work on it. It took 1 year to prove that it's wrong. But we proved. We proved that the transition, in fact, the transition is not discontinuous, it's continuous. The problem is that people do numerical simulations. And when you do numerical simulations, that's why I'm very careful in the message I'm passing to you. I already showed two things. Is the fact that some networks are very small and you can commit mistakes when you analyze them, or if you do numerical simulations, you should know what you are doing. And in fact, because the exponent that controls the transition is very, very small, the transition seems discontinuous, but is continuous in fact. It should be proved mathematically. We did it, okay? Another important concept, maybe you already, some people measure in networks, is this concept of key core. Key core has to do with parts or subsets of the network where the nodes inside of this subset has a minimum degree, okay? So it means that these cores here are strongly connected, and certainly these subsets of network play a role in the network. And people find that, in fact, it happens in many systems. After we publish this paper, many things appear, so we published this paper with this data here. So we proved the kind of transition. We described transition mathematically, and then people start to realize that, for instance, on neural networks, it also appears here. You see, the transition is discontinuous, as we saw. But it can be, for instance, in a very known problem in physics, that is glassy dynamics. They also claim that there is a square root singularity on the transition, and this is precisely what we have in this key core. Or it can be in jamming, the things you feel every day. So there is also a transition. This exponent, they found it numerically. This is numerical simulations, but there is this discontinuity, you see, and they found 48 0.48. We found 1/2, so very close inside of the arrow. But can be in evolution also. If you read here, they say Goldsev et al., so it's our paper, as a selection mechanism, key core population is systematic, so they claim that key cores can explain this thing of evolution. But can be also in information spreading. So when you want to pass a message, if you pass this message to some of these nodes, so the nodes that are inside of the key core, for sure the message is more effective in spreading. Or in proteins also. So there is a paper in Nature, in Proteomics, 2005, where they show that these central proteins, so proteins that are in these cores, play a special role. I will not go in details, but you can look in this paper. Another interesting thing is the following. Everybody studied networks. Metabolic network, protein network, genome network, etc., etc. But you know better than me that they are all connected. So the thing is, how can we study this system all together? So put all together, proteins, metabolic, genomics, etc., put all together and see, because there are connections between all of them, and see, for instance, the effect of diseases or drugs or whatever when you take a pill or something like that on this global network. So nowadays, we are interested in studying these multiplex networks, as we call, okay, or interdependent networks. So there are different networks that depend on each other. It's much more complex, the problem. For instance, you can see an example here. You have oil, gas network, electricity network, communications network, banking, financing, government, emergency transport. So all these networks, you can study each one by itself, like airplane network, people study, or the electricity network, people study. But put all them together, because they are all depending on each other. If one fails, maybe the other fails. And a good example of it is, for instance, this blackout in Italy. What is it? You have connections of power stations, electrical power stations, in the country. Here they are. And you have a network of computers that control these power stations. If one power station falls down, there is no electricity for a certain number of computers. Then these computers fall down. If these computers fall down, maybe one of them control another power station, and so on and so on. And so there is a cascade, and it happened that a big part of Italy was without electricity. But it happens in many places, in New York State, etc., etc. So there are many blackouts, and because of this effect, because there are many networks interdepending on different levels, and they can affect each other. This is also very interesting to study nowadays, but I will not enter in details. Well, to finish, it's something we are doing more recently. It's about neural networks, and network, as we can see here in this paper, in Nature Review Neuroscience, brain is a noisy processor. Sources of noise. And then we have here different mechanisms. So we see, we feel, so we excite muscles, we see things. So there are many ways to make noise in our brain. And so our ideas was to study this kind of networks with mathematical models. So we propose model, and so the idea is to understand mechanism of emergence of network oscillations, the impact of the noise and damage on collective dynamics of neural networks, phase transition, so many people observe continuous transitions or discontinuous transitions on the brain, neuronal activity like bursts, avalanches, etc., these resonance phenomena, enhance the detection of weak signals, stochastic resonance, etc., etc. So there are lots of observed phenomena, and we try to model it by our network understanding. So we propose an exact cortical model for neural networks. So we have excitatory neurons and inhibitory neurons, so we put it in this ratio, but you can choose the ratio you want. It's a parameter. So 75, 25%. And also include short noise, okay? So exterior noise to the network, you can control it with a parameter. And so we can make exact calculations, but we can also make simulations until 100,000 neurons in computer, and so you can compare results, etc., etc. So I will not go in details about the model, but you see, we can describe the density. This is the density of a certain type of, it can be excitatory or inhibitory neurons. A can take two values, inhibitory or excitatory. So this gives you the change of the density in time of this excitatory or whatever. And in this function here, that is not explicitly shown, you introduce the kind of network you want as a substract. So you have to assume that the brain is a scale-free network, or you have to assume that the brain is a random network. You put what you want. So the model is general. So you have some parameters here some parameters in the process, but they are described by quantities that we define. So some probabilities for this problem, but I will not show you here. But you see, we immediately find a phase transition for this density, controlled by some exponent. We can find the avalanches. We can study the size, the distribution of sizes of these avalanches. And you see it goes analytically as 3 halves. It was shown here in this paper by Beggs and Pless in 2003. They make measures, real measures, and they came to this result that is 3 halves, in fact. Okay, so the prediction is the same. We can, for instance, by simulations, I can show you here the blue and red symbols. So red here is black. You can see the change, the appearance of oscillations, even in a system with very few, say 50, only 50 neurons. You immediately see that there are some oscillations, but if you increase the size, you immediately start to have nice curves, and you have this oscillation either for the fraction of inhibitory or excitatory neurons. But you can even plot a much richer phase diagram where you have different regions, as you can show here, and depending on where you are in these lines, etc., you have hysteresis, discontinuous phase transitions, bursts and avalanches in some places. You have sharp waves. You have solenoid bifurcation along this line. You see, you can find all kinds of behavior people claim exist in the brain. In a simple model, you can put all together. Well, just to, you know this better than me, for sure, there are lots of models since the 70s. People try to understand but in general are models made in a different way. So it's a kind of electrical, it's like in physics doing a circuit, and you have resistors, you have voltages, you have intensity, and then you make some kind of models, I would say macroscopic models, to studying signals in the brain. We did it in a different way. We assume that there is a network. We put, we know there is neurons. There can be different kinds of neurons, and then we describe the system as it is. If you want to see, these are some papers we already published, so they are in archives, so you can have a look if you have interest. Okay. So I'll stop here. Thank you very much.
Questions? Yes. Where are the microphones?
Hi, I had a question about, so say all these kind of properties that you can measure about these networks.
I can't hear you.
Oh, sorry. So you have all these kind of properties that you can measure about these networks and that you see similarities between different systems. What I don't understand is how these measurements help us to better understand evolution itself. So how this feeds back again to biology in these major transitions.
Well, I told in the beginning that I hope the only thing in common with evolution is the title of the book. I prevent myself to that question. No, I mean, for me, evolution is not only biological evolution. Okay, evolution is a general concept, as I show you. I show you an example of, in detail, because the others you know better, of the evolution of language, you see? But in biology it's the same. However, nowadays you see that things seem static, protein networks seem static, but there was an evolution until there. You can guess how things evolved there. And this is our role, is to understand the beginning, or at least given we are in the present state, how this approach to this state. And so the models are somehow to show you this possible mechanism for that. I mean, but we never know, you know.
Okay. Two questions. One is there any way to predict in a percent value how much of the nodes should a system have to lose to collapse in a percentage?
Yes, it is. I show you that.
And it is always independent of the scale of the number of nodes, or there are some upper limit for this prediction?
No, it's I can tell you in the fraction. It's a kind of fraction of nodes you have to delete. So it's normalized by system size, yes?
Okay.
Okay, normalized by system size. But so, if you give me the system and I know the properties of this system, so you can ask me, why nature seems to be organized in such a way? So why nature seems to organize or as a structure when you analyze as a network of the kind of power law, okay? Because it seems, as I show you, it seems that in terms of resilience against attacks, and in principle, we have random failures, not intentional attacks, unless you take a pill or something to kill you, but it's not supposed to do that. I mean, when you take an aspirin, it's not supposed to destroy yourself, you know? It will certainly interact with chemically in some places, but not kill you, okay? So it means that it's a kind of random failure somehow in some place. So as an effect, but not as a strong effect. And so it seems that nature is prepared for these kind of failures, random failures. When we talk about specific things, then this kind of structure is not good, as I show you. Right? When you talk about scale-free networks, intentional attacks are dangerous because you can destroy the communication or whatever.
Okay. Now my second question. Thinking about evolution, can we think about a minimal number of nodes to add to a network to transform it in a next level, a new species, for example? I don't know, from one genome to another genome that defines a new kind of system with new properties that makes essentially different from the one that preceded.
Hard to say. Cannot answer.
Okay, thank you.
Okay, well, thanks for the talk. I have one comment and one question. So the comment is a bit like answering his question, like about the relevance of this kind of research for the major transitions in evolution. And I see that it's not really just the name, it's really about how bifurcations, which are like phase transitions between different states of a system, happen. So the major transitions in evolution are bifurcations in how the dynamical system of living beings changes and gets new properties. So I think it is really relevant. And in terms of what you explain, it's like a general property of the systems, so it can be used for many different aspects. So that's why I think it's really interesting. And the second thing is a very technical question.
However, I feel that sometimes biologists don't accept it very well.
Well, I like it, and I'm a biologist, but, well, I don't know. I only speak for myself. The second question, well, the question is just, you talk a lot about measuring these transitions with the degree, but I don't know, do you get any more insights if you use, for example, derived measurements like betweenness centrality and things like this? Mm-hmm. Thank you very much.
Well, because I like to do things rigorously, so I try to stay in my field. I mean, in my field, I'm in my space. So if I can't do things analytically or prove things analytically, so I avoid them. And betweenness centrality, it's a nice concept, of course, but it's not easy to do many things with this. I mean, analytically. In computer is okay. Like communities, for instance, people nowadays is very famous study communities that use a lot this concept of betweenness centrality, because if you go to this U.N.A.M algorithm, it's basically based on betweenness. You choose the node with highest betweenness, you remove it, and then you start to spread things in parts, and you find communities. But the concept of community, you cannot describe it mathematically. There is no definition of what is a community. It looks communities, no? But maybe if you delete a part, still looks a kind of community. So nobody can do analytical things with that. Then it means I didn't work on that.
Yes, thank you very much for the talk. I wonder if in the field of synthetic biology, where the aim is to put the minimal parts that can function for a pathway or even a living cell, has been this approach of considering a network that is robust has been applied? Are you aware of anything like that?
Well, as I said, I'm not a specialist and I don't know all literature, but for sure it was. For sure it was. I can tell you a reference, but for sure it was. There are so many things were made on this field, so for sure. Maybe someone can help here, I don't know. I don't know these things on literature, but I would say with 90% of sure. Here's the question. So, this is for you.
Desde aquí, gracias. Muchas gracias. Hay que conectar sí, yo me estoy congelando. Lo están entrevistando. Desde acá voy a hablar, ¿eh? Pero esto, quítenlo. No, lo voy a pasar desde acá. Sí, sí. Pero quítalo, bueno. No es un cable. Ok, déjalo. Ok,
Again,
nada más. apagar
Dr.
esto.
Ana Barahona is going to present Dr. Linda Manzanilla.
Este es para usted. Este es mío. Ya. Listo.
Mira, vamos a empezar, si por favor toman sus lugares. Bueno, mientras lo hacen, quienes se levantaron por un café, voy a empezar. The topic of this session is pre-Hispanic culture and society, and I would like to say a few words. Mesoamerica is one of the 6 areas in the world where the transition to archaic states took place. Founded in a diversity of landscapes and people, Mesoamerica constructed a common tradition incorporating different ethnic and linguistic groups. Mesoamerica is the region extending from central Mexico south to the northwestern border of Costa Rica that gave rise to a group of stratified, culturally related agrarian civilizations spanning an approximately 3,000-year period before the European discovery of the New World by Christopher Columbus. These some of these complex cultures advanced pre-Columbian Mesoamerican civilizations such as the Olmec, Teotihuacan, Maya, Zapotec, Mixtec, Huastec, Purépecha, Toltec, and Mexica. These indigenous civilizations are credited with many inventions, building pyramids, temples, mathematics, astronomy, medicine, writing, highly accurate calendars, fine arts, intensive agriculture, engineering, an abacus calculator, and complex theology. They also invented the wheel, but it was used only as a toy. In addition, they used native copper, silver, and gold for metalworking, in which they used very advanced methods. The biggest Mesoamerican cities, such as Teotihuacan, Tenochtitlan, and Cholula, were among the largest in the world. These cities grew as centers of commerce, ideas, ceremonies, and theology, and they radiated influence outwards into neighboring cultures in central Mexico. The professor Linda Manzanilla is a researcher of the Institute of Anthropological Research here at the U.N.A.M. She has participated actively in the formation of many generations of archaeologists in the National School of Anthropology, la Escuela Nacional de Antropología y Historia here in Mexico. Her work is related to the emergence and change of early urban societies in Mesoamerica, Mesopotamia, Egypt, and the Andean region. One subject that has been of her interest is the domestic life of the inhabitants of the first urban developments of archaic states, such as Teotihuacan, its government at the state and neighborhood level, as well as the detailed analysis of its multi-ethnic populations and the movement of foreign raw materials and goods. She has also developed an interdisciplinary research to study the multi-ethnic population of the Teopancasco neighborhood center in Teotihuacan, where traditional osteological analyses are contrasted with stable anastonium isotope to detect migrants, stable isotopes and trace elements to determine paleodiet, ancient DNA, as well as facial approximation. She has received many accolades. I just want to mention just a few. She received the Presidential Award of the Society for American Archaeology, the National University of Mexico Award in Research in Social Sciences. She is a foreign member of the National Academy of Sciences of the U.S. foreign member of the American Philosophical Society and member of the El Colegio Nacional in Mexico too. And she has received the Doctor Honoris Causa here at the U.N.A.M, and she has been member of the Committee for Research and Exploration of the National Geographic Society. So please welcome Linda Manzanillo, and her talk is Manzanilla, perdón, Manzanillo is a city here in Mexico. I'm so sorry. Linda Manzanilla, with the title Teotihuacan, an exceptional multi-ethnic city in Hispanic Central Mexico. Thank you.
Thank you. Could you please take out the lights? Lights off. Please, lights off. Lights off. Thank you. Well, it's a pleasure to be with you, many physicists, biologists, mathematicians, and I'm an archaeologist, an anthropologist also, who has been interested in one of the major transitions of past societies, from non-urban to urban societies, from chiefdoms and perhaps tribes or whatever other types of organizations to state societies. And well, the urban revolution, as characterized by Vere Gordon Childe, involves not only large concentrations of people in a settlement, in a huge settlement, but the fact that the population of those cities, first cities, was very diverse, heterogeneous, and also these people were devoted to tasks that are not related to food production. So you can think of ritual, you can think of the movement of goods, you can also think of the appearance of bureaucracy, of craft production, of many types of activities that are developed in cities. So this population receives the surplus production from the rural area, the hinterland around, but the fact is that it involved a major transition in human societies, in past human societies, because of all the different things that it involved. Of course, there are many types of urban settlements, and the ancient sites, the ones that we have as the first urban societies in past civilizations are, of course, located in Mesopotamia. And before the first cities, the proto-urban settlements involved that there were, you see here, tripartite temples for 2,000 years. Temple communities organized this surplus production and stored them in the storehouses around the sanctuaries. And this permitted the priests to have full-time craft production, to have movement of goods, to have bureaucrats, to develop the first traces of writing systems, of good control, of course, the plow, the wheel, not only for the transportation of goods, but also for the production of those vessels that were involved in the redistribution of food from those storehouses, and of course, the beginning of bronze production, metallurgy. So a lot of things were the byproducts of the urban revolution in Mesopotamia, and after 2,000 years of temples and the movement of goods by redistribution, we see the appearance around 3,000 before the Christian era of the first palaces. So the palace came after the first cities were already functioning in Mesopotamia, and the palace involved the beginning of a secular bureaucracy, a secular leadership with the amassment of wealth. This is how things happen in Mesopotamia, but nearby in the Indus Valley, in what is now Pakistan, we have huge, very large cities which had an orthogonal grid, that is an urban grid. They were very planned cities, but these huge cities did not have a particular leader on top. They probably had a co-rulership. They were multi-ethnic settlements, and we see Harappa and Mohenjo-Daro as enormous cities around 2000, before the Christian era, functioning as places where craft production was very important, where the movement of sumptuary goods was also very important. And they were very planned urban settlements with drainage systems, with many different urban services to the population. But they were what we called a corporate society, and a type of settlement, a type of society that is exceptional, not the common one that we see in Mesopotamia, that we see in Egypt, and in many parts of Mesoamerica. So my talk will be devoted to a particular city near Mexico City, which is called Teotihuacan, which has these characteristics: a very, very large metropolis with a corporate society, a multi-ethnic settlement, and which really was involved in a major transition in the basin of Mexico. So Mohenjo-Daro and Harappa in the Indus Valley can be compared as the exceptional societies in the Near East that may be compared to Teotihuacan, which is the exception in the classic period Mesoamerica. And of course, in Pakistan, in Harappa and Mohenjo-Daro, the movement of goods, even by sea, foreign merchants, the degree of craft production is comparable to what we see in Teotihuacan. The urban revolution in Mesoamerica had a precedent in Monte Alban, which is in Oaxaca, the first city in Mesoamerica around 500 before the Christian era. And this was the capital of a confederation of the three branches of the central valleys of Oaxaca. It was decided that the capital would be in the center of the three valleys, so all the three groups and the branches could have a capital. But let's see what happens when Teotihuacan begins to flourish in the basin of Mexico. The urban sprawl of Teotihuacan is 20 square kilometers. It's one of the largest pre-industrial cities in the world. As you can see, this Mexico City would be here, and all that stain is Teotihuacan. And it was a valley that received a large amount of people fleeing from the volcanic eruptions of the Popocatépetl volcano in the 1st century AD. And a large amount of people came to the valley because it had water springs, it had volcanic materials for construction. It was a valley very near the lake systems of the basin of Mexico. And after the arrival of these people fleeing from the volcanic eruptions of the Popocatépetl, many other people came to the city because there was, they could work in the city, as many migrants do. They could work in construction, in craft production, in the movement of goods. And this is Teotihuacan, the 20 square kilometer city with 125,000 people of different ethnic groups participating in an urban site. As you can see, even the San Juan River was channeled to follow the urban grid. The periphery of the city has enclaves of people, neighborhoods of people coming from elsewhere, the Oaxaca barrio, from people from the central valleys of Oaxaca, the Michoacan enclave, people from western Mexico, the merchants barrio from Veracruz. But inside the city, there were nobles of an intermediate elite of Teotihuacan bringing experts from elsewhere, from Puebla, Tlaxcala, Veracruz, Hidalgo, Oaxaca, Chiapas, to work in craft production for very special things at the city. The city was also a pilgrimage site. It was the capital of a state. It was a place that monopolized obsidian, from which all the technology was made. It was a place where the elite of Teotihuacan can do different rituals, different things. But the ritual at that time was a means to articulate all this diversity. There was a common god in all Mesoamerica, the thunder god that you have heard before, right now here. Well, that was the main god of classic period Mesoamerica. Leaving aside how it was called, it was the same god. So what you see, and contrary to what is present in the Maya area, where the dynasty, the king, is the central figure that you see represented in the archaeological sites, in Teotihuacan you see the contrary. Groups are more important than individuals. Fertility, the forces of nature are more important than the deeds of the dynasts. So corporate societies are mute about who are the individuals governing these types of society. We don't see them in the archaeological record. We don't know how many they are. So Teotihuacan was the main urban site of central Mexico during the first 6 centuries of the Christian era. But it left no written records. So archaeologists, as myself, have to plan an interdisciplinary strategy to find out what happened in this very interesting city. Obviously, it called upon people from elsewhere. It was an inclusive society. Multi-ethnicity was at the base of this society, but the visual recognition of who is who, from what regions they came, what office, what activities they did, or what ethnic group they represented was visually seen in how they dressed, how their headdresses were set, what type of sandals they wore, how they were painted. That was the visual recognition without a language spoken, because there were many languages at that city. So we have worked. Of course, there were the foreign enclaves in the periphery that you see with their funerary rituals are very characteristic from the regions they came from. They brought objects from those regions. They made imitations of those objects to emphasize that identity. To the east of the city, we have the Merchants Barrio, and that's the only part of the city where the Teotihuacanos allowed the people from Veracruz to construct huts as they did in their place of origin. In general, the city is very well planned. The Oaxaca people came to the city and they were building tombs as they did in Monte Alban. They had objects. Also the Michoacan people, they constructed multiple burial tombs. But of course, we see the different ethnic groups represented also in foreign figurines, in different representations in mural paintings, in objects that came from elsewhere, even in mural paintings where you see people from Veracruz with marine headdresses doing rituals in Teotihuacan. So it seemed to be a very heterogeneous and complex society, but ethnicity is one of the vectors. The other is office, and the third one is hierarchy. It's a very complex situation. And my proposal is that the rulers are not represented as they are in the Maya region or in the Oaxaca region at Monte Alban, because it is a co-rulership. So the corporate organization also involves the kind of rulership. And I propose there were 4 co-rulers in the city. And the main pyramids had different rituals devoted to the consecration of these huge monuments, different emblematic animals being set there, objects that came from afar as jadeite from the Motagua area in Honduras and in Guatemala, sacrificed individuals put under the pyramids to emphasize that they were building very important monuments, even places where different sacrificed individuals were set. But what we see is not only what I propose as co-rulership at the top as one of the characteristics of the corporate societies, but the first time we have in Mesoamerica multifamily apartment compounds. So people were living in places where different families had their own apartments, but contrary to what we saw in the Mayan area, I excavated some houses in Maya cities, huge Maya cities such as Cobá, where different families were sharing a common sanctuary for the ancestors. In Teotihuacan, each family has a ritual courtyard where the patron god is has its ceremonies, but it also has, each family has a kitchen, each family has a storeroom, places to work, dormitories, etc. But in each compound, in each domestic compound, there is a hierarchy. One family, one household is the main family of the compound, and here we see the one where we, in the compound we excavated, the one to the west is the main one. It has the patron god, its patron god is the storm god, that is the state god of the city, and there are, as we see in Mesopotamian domestic buildings, also in the Ubaid and proto-urban times in Mesopotamia, there is a hierarchy inside these multifamily compounds. And there are many types of multifamily compounds in Teotihuacan. As I said, the main family has the patron god as the storm god, but there are lesser status families with, for example, a rabbit as a patron god, as we saw there. Well, National Geographic drew my apartment compound in the 1995 issue, but we see different activities found in Teotihuacan. Craft production was very important. Of course, many common people were involved in building activities, in carrying weights, in cultivation elsewhere outside the city, in bird hunting, in butterfly catchers, divers and shell collectors. There were carriers and people moving goods. There were a lot of potters and people making obsidian tools. But there were craftsmen that had a higher status. Those are the lapidary people that worked finer stones, or the people tailoring the garments, the garment makers. And these different craft production scales of Teotihuacan involves ones that are in the domestic areas, others that are made in the periphery. Stucco, that is plaster, was made also in the periphery. There were crafts for the intermediate elites. As we see, these were the identity elements of each neighborhood, and there were crafts for the ruling elite. So we are excavating now this huge palatial compound between the two pyramids, where we see the corporate organization of rulership, which involved the movement of goods from afar, from Oaxaca, the mica, 35 kilos of mica. These rulers had also tailors, garment makers, and people working with pigments. The representations of these higher class elite? Well, we have few representations. Most of what we have in Teotihuacan are the neighborhood administrators, the intermediate elites, which are organized contrary to what is the corporate organization of the state at the higher level and at the apartment compound level, at the domestic level. So what we have is this middle class, which is competing one with the other, and who are tearing apart this corporate tissue of the city. This possible middle class are entrepreneurs, are people who are bringing from different parts of Mesoamerica the most lavishing or strange raw materials and adornments so they can compete with other neighborhoods and show their power. I excavated the neighborhood that is called Teopancasco, from which that mural painting comes from, which is very much related to the ocean. So you can see conch shells and marine elements attached to their garments. Other neighborhoods had other things. So the agents of ritual was very important in Teotihuacan to bring all this diversity of people together. There is the ruling elite and some guesses of where their palaces could have stand. We have some of them near the Ciudadela, others. Shala is the one I am excavating. Near the Pyramid of the Sun of the Moon. So none of the archaeologists till now have found the royal tombs of Teotihuacan. That is the problem of corporate societies, because these individuals get effaced from the representations, unfortunately, but it's an intellectual it's more interesting for us to find out who is who in this diversity. So I will briefly tell you how we did it in the Teopancasco Neighborhood Center, which has different parts, different sectors, one a main plaza with a temple and altar devoted to ritual, an administrative sector, the garment making area, which is a very specialized sector, the guard of the neighborhood, the residential area of the administrators, kitchens aligned to give food for all the workers, a medical facility. And this is the place that I excavated where this mural painting was found in the 19th century, where you see planting rituals from two different priests towards the altar of the site, throwing organic liquids with seeds. So we excavated most of the compound, and you see the huge plaza, the ritual plaza with the temple and an altar, and the different sectors where all this happened. So domestic ritual in Teotihuacan is very clear because it was a main force to attract people together. So we have found with chemical analysis of the floors how the ritual was made in the main plaza with these priests walking towards the altar, throwing organic liquids that left the phosphate anomalies in the floor, and the sandals of their walking in the stucco floors left the negative carbonate anomalies that you see here, the clear yellow things, because they were eroding the floors by walking with the sandals to and fro to the four cardinal points, and they were throwing these organic liquids with salvia seeds, what we call here in Mexico chia. So we have also found, with collaboration with Siena, that in the southwestern part of the ritual plaza, they were probably dismembering animals and human beings. They were decapitating human beings that we found in the ritual of decapitation at around 350 AD. 29 individuals were decapitated as a termination ritual. There are a lot of bones, bone instruments that come from human bones. So they were boiling bones, they were dismembering people, etc. The administrative sector involves stamped seals and also probably the tokens that the workers exchanged for tortilla and food rations each day in the neighborhood. The tailoring sector involved a lot of needles, of pins, to work those huge dresses and to attach to them conch shells and other marine elements. We have found at the site 14 different types of fish from Veracruz, particularly from the Nautla region, and even the mammal facial parts were cut to be attached to the headdresses. We have found some examples. So this neighborhood center also was involved in basket making, nets, lacquering of pottery with salvia oil, and the bringing of goods from many parts, not only fish and even crocodile, crabs from Veracruz, but pottery from Tlaxcala, pottery from Puebla. 32 families of conch shells are found at the site from the Caribbean Sea, from the Gulf Coast and the Pacific Ocean. So this middle class or intermediate elite was much involved in the movement of sumptuary goods to the city. And the osteological analysis of this population involved all these types of studies, and we have burial practices that are very much Teotihuacan, but others that are foreign burial practices at the site, such as the amount of decapitated individuals, each head put in a vessel and topped with another vessel, which is a characteristic of Veracruz. So these people coming from elsewhere, because we know that by the isotopic analysis, had nutritional stresses during infancy. So they probably came in the caravan system to have a food provision, a daily food provision at the site. With the Geology Institute of our university, stable isotope analysis, nitron isotope analysis was used to determine trophic levels, but oxygen isotopic analysis was used to determine the altitude from which they came from. We also did trace elements to know who had a marine diet from those who had a terrestrial diet. Oxygen isotopes permitted us to know who came from lower altitudes, even the coast, who came from middle range altitudes, and even higher altitudes than Teotihuacan. You can see here the comparison of trophic levels of the people of Teopancasco with the carnivores and the herbivores found at the site as animal bone elements. And we compared all these people coming from very different parts, were buried in different parts of the compound, even the altitudes from which they came, and the strontium isotopes that we did with the Luhis laboratory here at the Geophysics Institute allow us to see who were the migrants from afar, the ones that have a very different isotopic proportion in their teeth with respect to their bones. The teeth had the isotopic proportion of the places of origin sealed, and then the bone, as it is producing new cells, it has the isotopic proportion of Teotihuacan where they died. So here you see the migrants from afar clearly, and then the migrants from the corridor towards the Gulf Coast, and the people who are local have the heights of the white and black columns the same. But we also know by activity markers in their joints, rugosities that are the byproduct of the activities they made in life, that there were people carrying weights in the caravan system, people who were working fibers with their teeth and had this type of marks, people who were sewing in the garment production area, the people carrying weights with mecapal. As you know, there was no wheel in Mesoamerica, so most of the, well, all of the movement of goods was with people carrying them in there. So we have rugosities in their occipital and also in their cervical vertebrae. People walking large distances with the caravans had also their traces in their feet. And the ancient DNA that we did with the Cinvestab Irapuato allows us to see that the 4 haplogroups of Mesoamerica, A, B, C, and D, were present in this neighborhood from the onset. So we have a very diverse population working along, moving goods, doing craft production. We have even some of the facial approximation of some of these individuals done by forensic anthropologists. So we have more or less the type of people who were working there. And of course, the chemical analysis of the floors allows us to see, to emphasize the functional differences between the different sectors. We have crafts made, the painting of pottery, the painting of mural paintings, the lacquering of pottery, but also the working of such a vast quantity of shells coming from many parts. But we also know that they were painting their faces and their bodies with components that cinnabar, that are toxic. So there seems to have been a medical facility where they were mixing these toxic things of lead, of mercury, with others that allow them to reduce the toxicity. Of course, galena, which is the painting that the Egyptians used to paint their eyes, was present also here. And you see the peak with the lead there. We have different types of cosmetics used for paintings. And the most important thing is the affluence of goods and people from Nautla towards Teotihuacan, using this corridor that you see here. And of course, ethnic identity was important, and it can be reproduced in the urban setting. A hierarchy was also important, and particularly the neighborhood of Teopancasco was the only in all Teotihuacan with clear relations to the ocean. And their economic power also came from they brought cotton cloths to Teotihuacan for all the elite, which were thousands of people, for them to use, because the common people used agave garments. So the rulers of Teotihuacan are an enigma for us, but you can see that we are on the basis of a corporate society, very different from the Maya pyramid. And what I propose is the possibility of 4 co-rulers, and I am, as I said, excavating the Palace of Shala, where probably they had their offices. The 4 co-rulers had their offices there. We have these 4 similar structures around the temple in the center, and each of the structures devoted to a different deity. So their identity is diverse. And of course, there are a lot of materials coming from afar, pigments, mica from Oaxaca, a lot of things coming from elsewhere. And one of the co-rulers may have been the most important at the end of Teotihuacan history, because he was related to the rain god, which was the thunder god was the state god, and he normally uses goggles as the spokesman for the 4 co-rulers. So around 550 AD, all the central part of the city was burned because of a revolt from for me, from the intermediate elite of the neighborhoods. Why did they revolt? Perhaps the state was trying to control this autonomy of this intermediate elite, this economic power of these entrepreneurs, too late in Teotihuacan history, and there doesn't seem to be an invasion of foreign people to the site, so all the core of the city was set on fire, and the sculptures which were there were broken into pieces. This seems to have been a revolt. So Teotihuacan, this is the urban sprawl of the city, as you see here in the Basin of Mexico. And this kind of city, very well planned, was recuperated by the Aztecs in their capital, Tenochtitlan, 800 years after Teotihuacan, with an urban grid, a very strict urban grid, as you see in the Aztec capital underneath Mexico City. And of course, without an interdisciplinary approach, and a lot of people, students and other specialists, biologists, physicists, people working with genetics and with isotope analysis, this work cannot be done. Thank you.
Could we have the lights back up? So, yeah, something back there. Way back.
Dr. Manzanilla, first of all, I want to congratulate you for giving us a great talk. And my question is about the disappearance of Teotihuacan. And as spoken language gives society an identity of belonging, could it be possible that one of the many reasons of disappearance of this culture was a lack of a common language?
No, I think there was a main group in Teotihuacan, the Teotihuacanos, and we don't know what language they spoke, because the very simple glyphs that we have from that civilization is not comparable to the huge amount and complexity of the Maya written script. Here we have emblematic glyphs, very simple glyphs. And my explanation is that in a multi-ethnic setting, these simple glyphs can be read by different linguistic backgrounds. For example, I can set a very simple example. If you see a mountain with a grasshopper on top, you could read it in English as Grasshopper Hill. You could read it in Nahuatl as Chapultepec. You could read it in Spanish or in whatever language, because it's a very simple thing. A hill and a grasshopper on top. It's a toponym. So that's the type of thing we have in Teotihuacan. They can be seen and read by people from different linguistic backgrounds, and that is the normal case in multi-ethnic settings. There is no dominant elite that in a corporate society, you don't have a dominant elite that states that they have the most complex and sophisticated knowledge of script or whatever. This is a society that shares many things. Of course, what you don't see in what I said is that most of these workers that came from different places and worked in the neighborhoods, they were in very difficult conditions. Their joints, you can see that they were squatting for long periods of time. They were working with their hands or their teeth or whatever for long periods of time as they left traces in their skeletons, and we can study those. So I think Teotihuacan amassed a lot of people. They called upon a lot of people, but of course, they were fed on a daily basis. ration system as we saw in the Mesopotamian case, but perhaps not in the best conditions that you can imagine. Of course, that's life of migrants in huge cities, the same you see in modern cities.
I greatly enjoyed your talk. Of course, I'm not a specialist. I have two questions. The first one is general. When there is the passage from non-urban to urban society, as this has been studied in very different areas, I wonder where there is a critical size of the number of people who have to be together to create that. So, or is that very different from area to area?
One by one. It's very different from area to area because the first cities in Mesopotamia had around 50,000 people. And here you see Teotihuacan, not the double, more than the double of the Mesopotamian cities. You have different sizes, different conditions, but the clue is that the city is involved in providing services to rural hinterland. They are not involved in food production or in a very low scale, perhaps in gardens. The city is a place where you do many things that not related to food production. Food processing, perhaps, but the movement of goods, you do craft production in a huge scale, and bureaucrats appear, and of course, ritual specialists, militia, etc.
So you need at least 50,000 people, let's say, or there are data also of
50,000
less?
in Mesopotamia, yes.
At least, yeah. And the second question was concerning the heterogeneity of the people in Teotihuacan.
Yes.
So you mentioned that they had different languages, different way of dressing. So I asked whether they had experience already living in a city somewhere else when they came to Teotihuacan, or was the first experience of living in the city?
We have to ask them, and we don't have the time tunnel to do so. So that's one issue that we cannot know. If in their former regions they were living in small centers, urban centers, or not. They are specialists in craft production. That we know because we can study their skeletons, and they died in Teotihuacan. They were specialists, but they had nutritional stresses in their places of origin. So perhaps the fact that they migrated is because they were looking for better living conditions.
Thank you.
Evelyn.
You said that Teotihuacan was abandoned in 600, right? It was.
Yes, more or less. It was
the
fire in 550 and the abandonment of the site around between 600 and 650.
And why is that supposed to happen so early?
Why did they abandon?
Yeah.
Because the system collapsed. This system, this urban site, was the hallmark, was the Rome of central Mexico, as you have to imagine. It was the place where everybody came. It was the example of the most sophisticated Tolan, the city, the archetypical city of Mesoamerica. It was the place where very fine crafts were made. It was the place where you see people from different origins, where you meet. Well, one thing I have to say, we have seen in Teotihuacan that not everybody was allowed to move from, for example, in the Street of the Dead, what the Aztecs called the Street of the Dead, because the name Teotihuacan, Pyramid of the Sun, Pyramid of the Moon, and Street of the Dead are Aztec names. The Aztecs came when the site was abandoned, was an archaeological site, 800 years after, and they named the site Teotihuacan. But what we see is that common people are attached to their neighborhoods. They live there, they work there, they did their ritual there, their tianguis or market experience near the neighborhood. And only the elite, which were thousands of people, moved to the Moon Plaza, the Sun area, the Ciudadela. That was the place where the elite met, where the elite did ritual. Why do we know that? Because recently in the La Ventilla neighborhoods, on top of the streets, you have control stations, places that do not allow people to move around freely. So it's not a cosmopolitan site. It is the most dynamic sector of Teotihuacan are the neighborhoods. These are the ones competing. These are the ones moving goods from many different parts, bringing people. The upper elite, the ruling elite, is involved in their matters with the thunder god, etc. The people on top, on the bottom, are involved mostly in craft production and in construction. But the ones competing are the ones in the middle. And they were tearing apart the corporate organization of this. That's exactly the behavior of what is contrary to the corporate organization. Of course, when the city, the main part of the city was burnt and the ruling elite left, afterwards all the craftsmen left. And of course, the intermediate elite had nobody to work with them, so they left also. And people from the Bajío region came to loot. We have their behaviors in the tunnels under, near the Pyramid of the Sun. We have excavated those, and we know that they came from the Bajío region. They didn't like the city, they were not involved in that tradition, so they looted the site.
So, well, first of all, thank you for making us all Mexican to be proud of these amazing cultures. And, well, my question, I think, is very basic. It is obvious that this was a very developed, complex society. So how come there are no written records? I mean, is there a theory on how they might disappear? Because I think that they may have existed at some point. Did they disappear, or why didn't they existed?
The most complex writing system in Mesoamerica is the Maya, as you know. But mostly those records, leaving aside the astronomical records, are records for recording the deeds and the life of the rulers, are what Joyce Marcus called political propaganda. So if you don't have the system here, you don't need those types of records. You need recording, you need administration, but mostly with tokens, with things that are material, as the ones we saw. And this type of behavior, we see it also in Mesopotamia. The appearance of tokens in Mesopotamia predate the first cities for 5,000 years. We have them in 8,000 before the Christian era. Tokens are important because you see, you don't need to talk. You see things. They are not exchange media. They are things that allow you to move things, to see who is who, and they are material objects. So perhaps the Teotihuacanos had codices, but they have not reached us in the archaeological record. If they were made of amate paper, we have not them in the material record. So perhaps they did paint very simple things in codices.
Okay, the gentleman in the back who's had his hand up so long, probably his hand's gone.
Thank you. Why do you think that this urban revolution occurred in these specific places of the earth and not in other like Australia or most of Africa? Were there any factors here?
Yes, one factor is intensive agriculture, which is very important in Mesopotamia, as it is in Egypt, as it is in the Andean region. as it is in Mesoamerica. Intensive food production, intensive agricultural systems, and of course, in the basin of Mexico, where the first urban sprawl, as Teotihuacan was explained, we are now living in the last of a whole set of urban developments, always in the basin of Mexico, always multi-ethnic metropolis, huge megalopolis, always in the basin of Mexico. It involved a large amount of resources from different altitudes. It involved a huge lake city system with water provision as well as springs. There are a lot of elements that allow a huge concentration of people. So elsewhere you see valleys, as the Valley of Oaxaca, which with a huge, well, at that time it had a huge river system that was very important for the appearance of Monte Alban, even though there, Monte Alban was set on top of a hill as a political decision to have the capital in the intersection of the three branches of the Central Valleys. In Egypt, they did the same thing with the first capital. Memphis was set precisely where the delta intersects with the valley. Egypt had two different political systems before the unification, and the capital of the unified pharaonic state was set precisely in the place as a political decision where the two polities are intersected. So there are some cases where those are political decisions, but this is a huge valley with a huge city underneath. After Teotihuacan fell and was abandoned, what you see is different small urban sites set on top of hills with defensive walls, with many things that allow you to see that they were competing for territory. So what you see is that the corporate society did not last for long. It was a pact, a multi-ethnic pact, but it was broken by the behavior of the intermediate elites. So there are different types of cities and different factors for which you have huge demographic concentrations.
Okay, do you have a question? No? Question here? No? Okay, over there, there's several questions over there.
I have two questions. One, oh, it's two questions. One is, how do you know about the languages? You don't have a written record. How do you know?
Well, we in the foreign neighborhoods, we have some glyphs from Oaxaca in the Oaxaca neighborhood, in a stele and in different stone monuments. In that foreign neighborhood, we have some glyphs from Oaxaca, but they don't say much. They say perhaps a date, but written with glyphs from their region. And the rest of the glyphs we find in the city are emblematic. That is, glyphs that may be related to groups, only to groups, but they don't say much.
Yeah.
Not that as phrases as we have in the Maya region.
My other question is, what do you know about the gender relations?
Okay, so what we have is that in the multifamily apartment compounds in the domestic domain of the cities, we have, well, the women and men and children buried there and working there and doing activities there. But in the neighborhoods, in the neighborhood center, that's mostly a realm for men. We have only 15% of women buried in those neighborhood centers. So women, except if they were very specialized and very high standard craft producers, they were buried there. Mostly men are buried there. So you see that it was not fair. Women had their domain in the domestic domain. There were also some representations of elite women and even priestesses doing the planting ceremonies. But in general, the neighborhoods were a place where men were interacting.
Okay, there are two questions here, and then we'll go back over.
I know that you've been studying the urban developments of many cultures. So, talking about neighborhood and spatial organization, is there something crucial that is shared by all ancient multi-ethnic societies?
Well, what I can say is that I don't think that in the Indus Valley capitals as Harappa, Mohenjo-Daro, Chanudaro, and all the cities that you see in Pakistan in the Indus Valley civilization, this neighborhood approach has been used. They have excavated the architecture, and they have seen that they don't see palaces, and not even temples have been defined in those cultures. They see craft-producing areas, but I don't think that they have delimited neighborhoods as we try to do it here or in other sites. So the neighborhood approach is a very recent one in archaeology. It's an intermediate level between the activity areas and the site in the whole or the region. This intermediate level is not very easy to work upon. So what I have done is to locate the neighborhood centers. And that is more easy because we see public architecture, we see huge plazas, huge temples, and then we begin excavating and we see the craft producing areas, the military personnel, and all the other sectors.
Okay, there,
Okay.
and then, yeah.
Well, I enjoyed very much your talk, thank you. Geographically, where were the pyramids of the sun and of the moon located regarding the different the areas, these neighborhoods that you mentioned? Where they were located, the pyramids of the sun and of the moon?
The 4 sectors?
Yeah, the 4 sectors. I mean, and the second point, maybe it's related. It's, do you know, it's a clue of who built these pyramids, actually? Were there slaves, or the pyramids of the sun and of the moon that actually are part of the Teotihuacan, who built this?
Well, the first thing I should say, well, the pyramid of the sun is in the northeastern sector, and it is devoted to the thunder god. Even though the Aztecs that came 800 years after called it the Sun Pyramid, it was devoted to the thunder god, which was the state god of Teotihuacan. The Pyramid of the Moon is located to the north. You see it here. And it is the main temple of the northwestern sector of Teotihuacan.
Were they used by that time as ritual centers?
As temples.
As temples.
They were built as sacred mountains and temples.
And these neighborhoods use them? I mean, is this something that they share?
No.
Who used them
That's the issue. Originally, the first temple that was built, was the Sun Pyramid. Why? Because this valley received the people fleeing from the volcanic eruptions of the Popocatépetl. So what they did is construct a temple of fertility, because at that time in the classic period, the thunder god was also the earth god, the fertility of the earth. So they built the counterpart of the other god that was vomiting volcanic things and destroying sites. This was a place to counteract the destructive forces of what from which they were fleeing. Even in the 16th century, the Pyramid of the Sun, and you see it in the Relación de Teotihuacan, it was the place of the god of sustenance, of things that you eat. So it was a place where fertility was propitiated. So when the city developed in 200 AD, you see the urban grid functioning. The Pyramid of the Sun became the main temple of one of the quadrants of the city, one of the quarters, the northeastern one. The northwestern one had the Pyramid of the Moon as the main temple. So the elite that was set there had the Pyramid of the Moon of their temple. Not all the people were flowing to do cult there, only the elites. But they were based in each quadrant, these elites. So from those quadrants, the 4 co-rulers came to co-rule.
And is it known who built these pyramids?
How could we know? Many people, 20,000 people working. They were the first temples were built to counteract the destructive forces of the eruptions. So who built them? All people who were scared built them, because of course that was a place to do cult. To organize a new settlement, to establish a new city from people fleeing from elsewhere. How can we know who constructed them? I think that many people participated. That was a major catastrophe in central Mexico, the one in the first century, a major one, because we have the Universidad de las Americas has excavated the sites that were abandoned in the Puebla-Tlaxcala region. And all these original formative sites had constructive systems that were afterwards replicated in the city of Teotihuacan in a monumental level. The same talud tablero construction system, the disposition of 3 buildings around a courtyard with an altar, all these things were replicated in the city, so these people fled to the valley. Yes.
I just wanted to know if there was any breathing between these neighborhoods you described.
Any breathing? Well, that's one thing that I asked the geneticists. If people that were doing different types of burials and that had different haplogroups and different origins had offsprings, they were marrying without the intermediate elite knowing at those neighborhoods, but they are doing the phylogeny of each group. Till now, we really don't know.
Last question.
Linda, of course, it's very risky to make comparisons with other cultures, but 4 co-rulers seems to be a very unstable way of organizing something politically, and what comes to my mind immediately are the Roman triumvirates, where you have Lepidus, Pompey, and Julius Caesar, and so on. But on the other hand, I was thinking of the case of the Tibet, where people always speak of the Dalai Lama, but in fact there was the Dalai Lama and the Passion Lama, and they were elected independently, and they were really co-rulers.
Mm-hmm.
Is that somehow equivalent to how you picture the political organization of the...
Well, I think the opposite. I think co-rulership avoided coup d'etat in this huge heterogeneous multi-ethnic society. That was exactly the case to counteract the possibility of coup d'etat that you see in the Maya region. When they are competing for territory, you see one ruler conquering the other ruler to have his territory. So you don't see this here, except for one only event. And that involves the Feather Serpent group. The Feather Serpent had its temple in the Feather Serpent Pyramid, and that temple was destroyed by the Teotihuacanos in 300 and something. They are trying to date the event. The temple was, all these sculptures were torn from the temple. They were thrown to the soil, and then the temple was burned. And not only that, but a new platform was built so you could not see the face of that temple, the facade. So what could have happened? All the iconography of the Feather Serpent was effaced from the city, and what we see is that in 378, some 2 decades after this event, there is a Teotihuacan group doing a coup d'etat in Tikal, Guatemala, in the main Maya city at that time. That is very strange because this state did not have imperial activities. If not, we could have seen them in sites that are near Teotihuacan, not in Guatemala, so far from the city. So I have the idea that the people who were thrown, the people of the feather serpent, were banished from the city. They went to the main other city of Mesoamerica, in Tikal, and organized a coup d'etat. The Maya ruler died the day they arrived, and they put a Teotihuacan dynasty, a very short one, in Tikal, Guatemala, in the main Maya city in 378. So that was the only possibility. What we should imagine is that the other co-rulers did not allow the feather serpent perhaps to grab the political power of the city for themselves. They were trying to do a coup d'etat in Teotihuacan, but the other co-rulers did not allow them.
Okay, let's thank all the speakers and the questioners and